Alright guys, I wanted to take some time to solve this quiz that I gave in class on Wednesday because a lot of people did not do very well, despite the fact that this was very similar, if not identical, to the circuits that were on the homework. It's semi-discouraging to see really good homework grades and then really bad quiz grades, because it shows me that you're basically not getting what I want you to get out of the homeworks, and maybe that's because the homeworks are too easy. I'm not like playing around. Like it could potentially be that the homeworks just aren't challenging you, so when you come to class and you don't have LT Spice in front of you, then the quizzes are challenging. Anyways, we can talk about this in class on Monday. I just wanted to give a solution to this quiz for anybody who's curious why they got a 1 out of 5 and is just really lost on this RC circuit stuff. So let's just go at this from a base level. The pulse source, first and foremost, is going to start at 0, right? We have the pulse plotted here, and it jumps up to 1.8 volts after 8 nanoseconds. It stays high for 22 nanoseconds, so then it comes back down at 30. And we basically want to plot V out. So we know that this is what V in is doing. The question is, what is V out doing? And so I say, given the RC circuit and the input waveform, blah, 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 sketch the waveform for V out of T on the given plot. Be sure to plot and label the following specific data points. Okay, so the first thing to note is that there are 3 distinct time periods here. There are 3 distinct time periods. There's a time period before it pulses high. There's a time period after it pulses high but hasn't gone low yet, and then the time period after it pulses low. And we're going to have 3 different segments or pieces to our piecewise equation, basically, for this output waveform, because the behavior is going to change each time the input changes. Alright? So our first timestamp, I'm just going to write the timestamps up here, is basically going to be t less than 8 nanoseconds. Okay, so for t less than 8 nanoseconds, we basically are going to have one equation for V out of t. So let's call it V out 1 of t. For the next one, it's going to be between the rising and the falling edge of the input, which is between 8 and 30 nanoseconds. So this is going to basically be 8 nanoseconds less than or equal to t less than 30 nanoseconds. We're going to have V out 2 of t. And then lastly, we're going to have the time after the pulse goes low, like I said, which is going to be for t greater than 30 nanoseconds, or sorry, greater than or equal to 30 nanoseconds. And that'll be V out 3 of t. Okay? So we've got these 3 time periods, and V out is going to behave differently at all 3 time periods. Okay? So first and foremost, the first time period is the easiest, right? What is V out 1 of t going to be? V out 1 of t is just 0. When my input's doing nothing and it's sitting at 0 volts, nothing's going to happen to V out. Right? The capacitor's initially discharged, and we're going to have no behavior basically in the circuit. So if I were going to write this, I would write V out 1 of t is equal to 0. So that's my first equation. And that is the case as long as t is less than 8 nanoseconds. Okay? And my first point that I want you to plot is basically V out of 4 nanoseconds. That's less than 8 nanoseconds, so V out 1 of 4 nanoseconds is just going to be 0. So I can come right here and plot that data point at 0, right? Next, let's look at the next time frame. We have for between 8 nanoseconds and 30 nanoseconds. So that's basically when my input goes high. So when my input goes high, right, it's going to go from 0 up to 1.8 volts. And we know that the voltage across a capacitor cannot change instantaneously. Okay? The voltage across the capacitor was initially 0, right? And now my input pulses up to 1.8 volts. Well, if this side of the capacitor goes up by 1.8 volts, this side of the capacitor also needs to go up by 1.8 volts so that we can maintain 0 volts across the capacitor. Okay? So there's still 0 volts across the capacitor, but now what I have is I have 1.8 volts at V out, and I'm going to have 0 volts on the other side of my resistor. So I get a current flowing. I get a current, which is going to be 1.8 volts over 2K. Not super important, but that would be basically 0.9 milliamps. And that is equal to C dV dt, right? The voltage across my capacitor, because that's the current that's flowing through my capacitor. If it's not clear at this point that the current flowing through this resistor is the same as the current flowing through this capacitor, then you really need to go back and review, because this is a series loop. This is one single loop, so the current flowing in the entire loop is the same. Okay? So if I have, at this instant, 0.9 milliamps flowing through my resistor, I also have 0.9 milliamps flowing through my capacitor. Okay? So just all I want to note here is the fact that this current flowing gives rise to a change in the capacitor voltage. That's all I really want to know here. We're not going to go do any crazy calculus, and we're definitely not going to do any crazy calculus, because all we need to know is that my capacitor voltage is 0. There's 0 volts across the capacitor. There's 1.8 here, and there's 1.8 here. So basically what my waveform has done thus far is it's gone. Let me switch colors so that we can maybe see it better. I'll switch to red. It's gone 0, 0, 0, 0, and at 8 nanoseconds it shoots up to 1.8 volts. So that's right where we're sitting right now. We've got this. It's still kind of hard to see, but it'll be easier to see once it's not literally following the input. And so now my input is tied to 1.8 volts. So this node is not going to move. We already know it's sitting at 1.8 volts. However, current starts flowing and the capacitor starts charging. Okay? Just like I said, if this capacitor is charging, that means that the voltage across it is increasing. The voltage across it, the voltage difference across the capacitor. This is 1.8 volts and it's fixed there. So the output, V out, has to start going down, right? That would only make sense, so that the voltage across the capacitor could increase, right? This voltage difference has to increase, which means that this voltage has to start going down. And exactly how does it go down? Well, it goes down following the discharging equation, or the Fife equation in this case. Let's just write it out. Basically, V of t is equal to V final plus initial minus final e to the minus t over tau. Okay? So I know my initial value in this case is, because I'm looking at the node V out, right? My initial value is 1.8 volts. It's fair enough. We just determined that this jumps up to 1.8 volts. So I'm basically going to write V out 2 of t. This is going to be a different equation, and it's going to be based on Fife. My initial voltage is 1.8, and again the question here is going to be, what does V out eventually go to when there's no current flowing in the circuit? Well, when there's no current flowing in the circuit, V out goes to 0. Okay, so my final value is 0, so I can write out V final plus V initial minus V final, where V final is going to be, for this case, it's going to be 0. V final, or V initial, is 1.8, like I said, and V final is 0. And then note that I have a time delay of 8 nanoseconds, so I'm going to write this out as 1.8 e to the minus t minus 8 nanoseconds over tau. And what's my tau? It's R times C, so it's 2 pico times 2K, which gives me 4 nanoseconds. That is V out 2 of t, and that, what did we say? We said V out 2 of t holds true for all the times between 8 and 30 nanoseconds. Okay? So basically what's going to happen is we're going to get this, this decreasing behavior down to 0 over this time span, and it's going to follow this equation. Let me grab my calculator real quick, actually, so that I can actually calculate these values. I'll be right back. Alright, I'm back. Here's my calculator. So I'm going to go ahead and put this equation into my calculator. 1.8 times e to the minus, I'm going to use the variable x, minus 8 divided by 4. Okay, that's my equation. And now let me delete all these values. These are all, where's the delete button? Oh, right here. Hold on. This is just ridiculous. Delete, 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 delete. Okay, so what data points do I have that fall in this time range? I have 12 nanoseconds and 28 nanoseconds that I'm looking for. So let's plug in 12 and let's plug in 28. Okay, so those are my two voltages. Everybody see that? 0.662 and 0.1012. Okay, so I've got at, let me put this on here. At 12 nanoseconds, which is right here, I've got 0.662. This would be somewhere like right there. And then at 28 nanoseconds, I've got 0.012, so basically 0. Let's just put it like right there, just a little bit. And so now I can fill in this part of the curve. Basically it does something like this, okay? And so now I need to analyze what's going to happen when my source goes back down. My source is going to, it's at 1.8, and at this point now, I've got all these different pens. I'm trying to make this clear, but V out is now sitting at 0 volts, right? It's in steady state. V in is sitting at 1.8, right? And what's going to happen is my input is going to pulse back down to 0. Okay, so it's going to go back down to 0 volts. When my input goes back down to 0, the voltage across my capacitor, since my capacitor is charged, it's charged to 1.8 volts, right? So when this goes back down to 0, my capacitor voltage cannot change instantaneously. In order to maintain 1.8 volts across this capacitor, I need my output, which is sitting at 0 volts, to drop to negative 1.8 volts. Okay, so that's why this behavior happens, where the the output signal drops down to negative 1.8 volts. When my input drops, my output has to drop with it. Okay, and that's because the capacitor cannot change voltage instantaneously. Okay, oh, I meant to draw these points in black because those are the required ones. Okay, so this is basically at 12 nanoseconds, at 28, at 4, and now I have to do the other two, which means I need to make the equation, because again, what is V out eventually going to go to? It's going to go to 0. When there's no current flowing in the circuit, it's tied to a resistor to ground, so it's going to go to 0. So let's go to a green pen, and it's the last color I have, and let's see, what is the initial value? The initial value is negative 1.8 in this case. You see that? The final value is 0. Okay, so now the equation is going to be basically exactly the same thing. V out 3 of t, right? That's t greater than 30 nanoseconds, so all of this time it's going to be negative 1.8 e to the minus t, but now this time I'm not subtracting 8 nanoseconds of delay, I'm subtracting 30 nanoseconds of delay. Minus 30 nanoseconds over 4 nanoseconds, that's my V out of 3. Okay, so those are my three equations. And now let me go put this one into my calculator. I can basically just insert a negative sign, and it's the same equation, and change the delay to 30 instead of 8. Does everybody see that? So now I'll go back to my table, and now I'm not concerned with these values anymore. Rather, I'm concerned with V out of 32 and V out of 50. So plug in 32 and plug in 50, and I get negative 1.09 volts and negative 0.012 volts. Okay, so let's plot those points. At 32 nanoseconds, I get negative 1.09, which is basically right here. that right? 32, negative 1.09. Yeah, that's fine. And then at 50 nanoseconds, I get negative 0.012, which is basically 0. Okay, so my waveform is going to look like this, basically. Okay, so that's what my waveform should look like. This is at 32 nanoseconds, and this is at 50 nanoseconds. Okay, and if I wanted to write all the voltages, I could. I guess I will. So let's write them right here. I'll just go V out at 4 was equal to 0. V out at 12 was equal to, was it like 0.66 volts or something? V out at 28 is equal to, I don't know, it was like 0.012 or something. V out at 32 is negative 1.09 volts, and then V out at 50 is equal to negative 0.012. Alright, those are all my values, and I would be done with the quiz at this point. So, not too many people got this right. Actually, I was a little bit disappointed in the grades, but hopefully watching this video makes a little bit more sense what I'm doing and what I expect on these quizzes. When you do the homework, obviously, please try to actually understand what's going on with these waveforms. Just looking at them and guessing is not going to get you very far, especially because problems like this are going to show up on the final. I want everybody to do well on the final. Please be vocal, in class on Monday. If this stuff just doesn't make any sense, or if you guys feel lost, we can do a review. We can take it a little bit slower as a group. Obviously, if only a couple people are struggling with something, I can't stop the entire class, to recover something that only a few people are struggling with. But if most of you guys, as a general consensus, feel like this stuff is really hard and we've moved too fast through it, just speak up and we can do a review and kind of just go back over all this stuff from the fundamental standpoint, and maybe I'll try and re-explain it or explain it in a different fashion than how I've been explaining it, to try and broaden your understanding. Hopefully this helps. Let me know if you have any questions, and otherwise I'll see everybody on Monday.